We have dEt by ds, which is kappa times En. So what are these other two creatures? Let's take a look at dEb by ds. It's a vector, which means that in all possibility, this could have a component along, and okay. So before I jump into the fire, dEb, will it have a component along EB? dEb is perpendicular to EB. We know that for a fact, which means it cannot have a component along EB, but that does not preclude it from having components along En and Et. So it could have components along Et and En, but not along EB. And I'm going to recall some results from basic vector mechanics, which may not have been seen in some of your courses, but it's something that you've probably used a lot. I will write dEb by ds in the following manner: a component along the Et direction plus a component along the En direction. Okay, this is common sense, right? Because we just said it could perhaps have a component along these two directions. How do I find a component of a vector? I take that vector and I dot it with the direction. That's a component of a vector along that direction, right? So this is going to be dEb by ds dotted with Et. Once again, how do I find the component of a vector, of this vector, along the tangential direction? I take that vector and I take its dot product with the tangential direction, which will kind of siphon out its component along that direction. Let's take a look at this guy. Okay? Let me start off with the following equation. What's this quantity? Differentiate both sides with respect to ds. Still remains 0. Do the product rule. dEb by ds dotted with Et. dEb dotted with dEt by ds is 0. Or dEb by ds dot with Et. Minus EB dotted with dEt by. I'm going to make use of the result that dEt by ds is kappa times En. Okay, that's written right here. So this is minus EB dot with kappa En. What is EB dot with kappa En? It also has to be 0, right? Because EB and En are perpendicular to each other, so this is also 0. So which tells me that this vector does not have a component along the Et direction. That's the first thing. Likewise, dEb by ds. Look at this dot product, EB dot with En is 0. Do the differentiation with respect to the distance, infinitesimal distance. So d by ds of that is still 0. Use the product rule. Dn is minus dB dot with dEn. I'm doing exactly the same thing. I'm just taking care of the second component in this combination, which is this creature here. By definition, this cannot be 0, because if I have a vector, if I'm defining a vector, it has to have a component along a certain direction. Okay, so which means that this is non-zero. We don't know what it is, that is fine, but we're going to give it a special name. So dEb by ds is essentially this term here. En or minus dB En. And the term in the brackets, which we said is non-zero, is going to be called as tau, the quantity tau. Where tau is called as the torsion of a curve. So tau torsion of a curve. Torsion of a curve is the failure of a planar curve to be a planar curve. Does this make sense? Or let's say that if I have a planar curve, its torsion is 0. So essentially, if I have a helical body, right, there is, first of all, if I look at a plane on the helix, there is a curvature on the plane. But then as I am traveling along the length of the helix or the body of the helix, there is also a curvature that's coming out of the plane at any given instant in time. That curvature that is out of the plane is called as the torsion of the curve. And the in-plane curvature is your curvature cap. Okay, so those are the two things that you want to remember. So in some sense, this tau is the curvature that is emanating from the plane that contains the tangential and the normal vectors. Okay, so this is out of plane. And I draw a figure. Out of plane curvature with respect to the ET En plane. Right, so look at a tornado. I can draw a plane at any instant in time. I can say that, okay, this is the tangential direction. Then the direction that is perpendicular to ET and pointing towards the center of curvature at that instant in time is my normal direction. And the cross product of these will be my binormal direction, which is in this instant pointing up. You can see that at any instant in time there is going to be a curvature for that curve defined with respect to the ET-En plane, which is the planar curvature, and the curvature that is out of the ET-En plane, which is called as the torsion of the curve. And typically if you have a helical spring, its torsion is constant. Okay, and we will not be dealing with torsion for the time being, but we will go into the details of it as we solve some problems. So for the time being, it might seem like a hazy quantity. All you need to remember is the torsion of a curve to be, a failure of a curve to be planar is torsion. The failure of a curve to be a planar curve. Torsion can be positive or negative. Right-handed helix is positive torsion, left-handed helix is negative torsion. Once again, those details are things that we will not be seeing for the time being. Okay, so just hang on to that thought. And so this is now our third Franacery formula, fourth Franacery formula. Fourth one, dEB by dACC minus tau Dn. And the last one, which I'll just write out, but we will not prove. It is easy to prove it. Same way that we have done this now. The fifth one, dEn by ds is going to have a component along ET and EB. Dot with EB, dEn by ds dot with EB, and I'll prove this in my lecture notes that I'll post, but we are out of time. We have 2 minutes left. So this is tau EB minus kappa ET. This is the fifth Franacery formula. For the problem that we are going to solve on Thursday, we will assume that the problem is a planar problem because I'm solving a two-dimensional problem, which means that for us the torsion will be 0. Okay, so for a planar curve, tau is 0, and for a straight line, kappa is 0. And actually, these two are called the Venezuelan Theorems. It is common sense in some sense, but we will not prove them. It's easy to prove them too, of course, but that's not our point here. Our point is we want to make use of these ideas and see how can I solve some classical problems in dynamics. Okay? All right. So with that, I'm going to end the lecture, and I'll be happy to answer questions if you have it. On Thursday, we're going to use all of this to start a problem. Okay? And you'll see the utility of it.